Three heavy space vehicles are being developed by the National Aeronautics and Space Administration under the project name Saturn. The largest Saturn vehicle, designated Saturn V, consists of three stages. The S1C, using 5 F1 engines, the S2 with 5 J2 engines, and the S4B using a single J2 engine, plus the Vehicle Instrument Unit, and the Apollo spacecraft, which Saturn V will carry. This second quarterly film report will cover progress on the Saturn V vehicle during February, March, and April 1963, highlighting major effort concentrated in areas of final tooling preparation and initiation of fabrication. An important step in development of Saturn V's S1C stage, represented here by a 1/20th scale cutaway model, was work during this report period on fabrication of bulkhead components for the liquid oxygen and fuel tanks. The initial bulkhead gore segments were formed in early February by the Military Aircraft Systems Division of the Boeing Company at Wichita, Kansas. Heavy rollers first press sheets of aluminum alloy to the approximate required contour. Gore segments are made in two sections, base and apex, later welded together. The rolled sections are then placed in this large bulge form die for final precision shaping through use of liquid pressure in a rubber bladder. Water is forced into the bladder by a pump. As the bladder expands, it forms the aluminum against a plastic liner at a maximum of 1,500 pounds of pressure per square inch. Upon delivery to the Marshall Center, gore segments are first heat-treated or aged in a large oven for 24 hours at 325 degrees Fahrenheit to increase their strength and hardness before they undergo the fabrication and assembly processes which will result in a finished bulkhead. Marshall's bulkhead fabrication and assembly tooling underwent continued buildup and qualification during the report period, with work also underway on the first bulkhead, which will be part of a structural test fuel tank. This initial station in the bulkhead assembly line performs routing and welding for all gore fittings. The second tooling fixture trims the top edge of the base and the bottom edge of the apex of each gore segment in order to make a joint to weld the two pieces together. At the third station, this gore welding fixture is used to join the gore's base and apex portions. Mounted over a pit, the welding platform can be tilted 30 degrees since it is desirable to weld uphill at all times. At the fourth station, a meridian edge gore trim fixture is employed to perform the job of trimming the gore segments lengthwise. At station number 5, gores are installed on the bulkhead welding and assembly fixture where 4 operations take place: meridian weld, bulkhead base trim, bulkhead to Y-ring weld, and Y-ring to skin weld. 2 gore segments have been successfully welded together in the qualification operation. 8 gore welding for the first bulkhead is scheduled next quarter. Installation of the final station, number 6, was completed during the report period. Checkout of the fixture, which will weld in the bulkhead closure plate, is underway. The S1C stage partial tail section mock-up has been moved into Marshall's newly completed mock-up building from the adjoining shop where it was fabricated. After further build-up, the unit will be installed on its 4 support posts during the next report period, and the full-scale F1 engine mock-up will be attached. Manual gimbaling tests of the F1 mock-up have been performed to evaluate design of flame curtains, compression compensation, and cable installation. A 1/8 scale model S1C liquid oxygen tank is being used at Marshall to study LOX flow characteristics and to develop efficient anti-vortex devices such as baffles, screens, and standpipes. For testing, the tank is filled with water with dye added to enhance engineering photography. A rotating paddle is used to simulate vortexing, which might be caused by vehicle movements in flight, thus preventing sufficient LOX supply to engines. Construction of Marshall's Saturn V test facilities, such as this hydrostatic test and vertical assembly building, basic construction of the reinforced concrete blockhouse or control center, some 250 yards from the stand, has been completed, and interior work is progressing to accommodate the electronic test equipment which will later be installed. The instrumentation tunnel running between the blockhouse and test stand is complete and ready for installation of cables. The 40-foot deep excavation for Marshall's F1 single-engine static test stand has been finished, and preparations have begun for pouring the foundation. A contract was awarded in February for construction of the 105-foot-tall concrete superstructure. The west side of Marshall's S1 stage static test stand is now being modified to test F1 engines. This will allow start of F1 tests in November, several months earlier than scheduled. The position will be converted back to S1 testing after completion of Marshall's F1 test stand. A new series of experiments in rocket sounds was begun at Marshall this quarter, using a new and larger horn, replacing one which was moved to Marshall's Mississippi test operations. The huge horn, which simulates the noise of a Saturn static firing, is being used to learn more about the transmission of this low-frequency sound and to determine the most advantageous conditions for conducting static firings from the meteorological viewpoint. Experiments in partially suppressing the noise of Saturn firings are also being conducted at the center by firing a small engine into a specially constructed water tank. Microphones set up on a semicircle of 16 poles near the tank record sound levels during firing. Various deflector, cone, and baffle devices inside the water tank help to dissipate the energy which creates the noise. The tape-recorded sound is later analyzed by technicians to determine the effectiveness of suppression. A new jet impingement test facility was placed in operation this quarter to study the feasibility of launching space vehicles directly over a large body of water. Small solid propellant motors are presently being used in tests. Later, F1 models will be fired singly and in clusters. The stand is designed for up to 50,000 pounds thrust. Its platform can be varied from 0 to 10 feet above water surface. Portholes in the tank allow for photographic instrumentation. The tank is 51 feet in diameter, 24 feet deep, and holds 350,000 gallons of water. Splash effects, jet penetration depths, and effects of underwater deflectors will be studied. At the Boeing Company plant in Seattle, Washington, dynamic calibration tests using a 3/100 scale Saturn V model were performed this quarter. An electrical shaker device with rod attachment induced vibration under controlled frequencies and amplitudes. The same model, with weight suspended to introduce linear deflection, was also used in static calibration tests to measure vehicle bending moments. A 1/20th scale model equipped with 2 receiving antennas was used in command-destruct antenna pattern measurements to determine vehicle aspect angles over which the destruct signal can be received. At Marshall's Michoud operations in New Orleans, the first S1C stage Y-ring was completed by Boeing in mid-February using the recently installed 42-foot boring mill to machine the ring to precise measurements. Machining of the second Y-ring has now also been completed. The initial ring was removed from the boring mill for shipment to the Marshall Center, where it will become part of the structural test tank. Machine marks in the open V cut on the top of the ring were removed by hand grinding. The V forms the junction of the bulkhead and the intertank or interstage. The 2-ton ring was carefully wrapped and sealed to provide protection during handling and shipping. The ring was shipped by barge from Michoud on February 22nd and arrived at the Marshall Center 10 days later. Work on Michoud's S1C vertical assembly building continued this quarter, with relocation and installation of underground pipe and electric cables accomplished. The foundation for the hydrostatic testing and cleaning pad was also under construction. This is the last station for the booster before it is returned to the final stage preparation area in the main plant for outfitting. The VAB will have 3 turntables with the pits housing the turntable gears recessed in the foundation. When the building is completed, it will consist of 2 sections, one for booster assembly and the other for hydrostatic testing and cleaning. At Rocketdyne, F1 engine work this quarter included assembly of an experimental concentric tube injector. Prior to installing the faceplate, the igniter tubes are placed in the body of the injector. There are 21 of these elements, one for each compartment in the baffle. LOX tubes are inserted through the back of the injector. The concentric fuel tubes and the baffles are then installed on the face. In operation, oxidizer is swirled in the center tube to form a cone of spray. The fuel in the annular element is impinged on this cone and mixing occurs. Since injector elements are 8 different lengths, 8 flame fronts are propagated in the combustion zone. It is believed that this multiple flame front and concentric injection will increase dynamic stability. Testing of Model Mark 10 inducers was conducted in a water tunnel under various operating conditions. Instrumentation photography permitted observance of such phenomena as cavitation, backflow, and blade tip vortexing. At North American Space and Information Systems Division, contractor for the S2 stage, bulkhead tooling was being installed this quarter in the new Seal Beach, California facility, including the bulkhead gore segment welding tool, dollar weld tool, the autoclave, which will provide heat and pressure for bonding insulation to bulkheads, and the acid bath tank for the etching room. The S2 electromechanical mock-up, scheduled for first use in July, is being fabricated and assembled at S&ID's Downey plant. The mock-up will be used in 3 areas: manufacturing, to check placement of lines, components, and engines for interference and accessibility; testing, to check out compatibility of flight systems as units and with each other; and GSE development, to check out automatic GSE and make checkout computer tapes to be used with flight stages. Fabrication of the S2 battleship test stage, depicted here in model form, is proceeding on schedule. Initial use is set for the first quarter of 1964, marking the first time for J2 engines to be fired in cluster. Fabrication of the S2 structural stage, for use in checking entire vehicle structures, is also underway. At S&ID's El Toro facility, activated this quarter, high-energy forming tests have been successfully performed on waffle sections of the S2's common bulkhead. The part to be formed is embedded in a castable epoxy urethane. An explosive charge of primacord is used to provide the shock wave for forming. At Santa Susana, rough site preparation of the Coca area of Rocketdyne's propulsion field laboratory has been completed. The S2 battleship will be installed in test stand number 1. Test stand number 4 is being prepared for installation of the all-systems stage, the first flight-weight S-2 test vehicle. At Rocketdyne, contractor for the J-2 engine, common to S-2 and S-4B stages, a relatively new metal forming technique, electrolytic erosion, is being used in manufacture of J-2 injectors. The forming die, made of compressed graphite, acts as an electrode, and a non-conductive oil removes the eroded material. Build-up of facilities for the J-2 engine program at Propulsion Field Laboratory at Santa Susana continued during the report period with work on the liquid hydrogen storage area, run tanks, and horizontal and vertical static test stands. At Douglas Aircraft Company, Santa Monica, fabrication of production tooling fixtures for Saturn V's third stage, S-4B, was well underway this quarter. The first vehicle manufactured will be used for hydrostatic testing. A full-scale engineering mock-up is under construction for use in verifying flight-type system compatibility with ground support equipment. Both tank domes have been completed and installed in handling jigs. The forward interstage structure was attached to the forward dome and the aft skirt to the aft dome. Work is proceeding on design and layout of automatic checkout ground support equipment and its housing facilities. 4 complete sets of ground support equipment will be fabricated. The testing program in progress for S-4B includes research, development, qualification, production, and reliability verification testing. Construction of the S-4B static firing test facility, Complex Beta at Sacramento, is progressing satisfactorily. A contract for the battleship tank for test stand number 1 was awarded this quarter. At Huntington Beach, construction of the Douglas Space Science Center is also underway. This facility will include an assembly and hydrostatic test tower, mock-up and fabrication building, space simulator, and S-4B systems integration area. Structural design layout of the Saturn V instrument unit, which will be located between the S-4B stage and the Apollo spacecraft, is in process at the Marshall Center. Guidance and control, tracking and telemetry equipment will be mounted around the periphery of the unit, which is 3 feet high and 21 feet 8 inches in diameter. Circulation of a coolant through panels will provide temperature control. The unused volume in the center will allow the legs of the Apollo's lunar excursion module to extend into the instrument unit, thus shortening Saturn's total vehicle length.